Hey everyone, and welcome. Today, we are pulling back the curtain on the magic that's happening inside every single digital device you own. We're going to explore the circuits that let machines think, process, and, maybe most importantly, to remember. It really all boils down to this one simple but honestly pretty profound question. Your phone, your computer, they hold onto your photos, your messages, everything. But how? There's no tiny little brain in there. The answer? It's all about pure, elegant logic, and today we're going to build it all up from scratch. So, here's the game plan. We'll kick things off with the two big families of digital circuits, then see what happens when we add the whole concept of time and memory. After that, we'll meet the tiny little component that makes it all possible, and finally, we'll see how this all comes together in the real world. Okay, let's dive right in. When you zoom all the way out, every single complex digital circuit you can possibly imagine, I'm talking from a pocket calculator to a massive supercomputer, belongs to one of two fundamental families. So, on one side, you've got combinational circuits. With these, what you put in right now is exactly what you get out, instantly. A simple calculator is the perfect example. You hit 2 plus 2, and it immediately gives you 4. It has absolutely no memory of what you did 5 seconds ago. Then on the other side, you've got sequential circuits. Now these are different. Their output depends not just on what you're doing now, but also on what happened before. Think about a basic light switch. Flipping it does one thing if the light is off, and the complete opposite if the light's already on. See? It remembers its last state. All right, so let's explore that first family, that memoryless world of combinational circuits. This is really where the heavy lifting, the actual doing part, happens in a digital system. That's the formal definition, but a better way to think about it is that these circuits are all about pure, unadulterated action. They're built from basic logic gates, ands, ors, nots, and they live completely in the present moment. There's no past. An input shows up, a logical operation happens, and an output shoots out, all in a flash. And these things are the real workhorses of the digital world. Think of them like specialized little workers on an assembly line. You've got circuits for doing math, like adders and subtractors. You've got data routers, things like multiplexers and decoders that are basically traffic cops for information. And then you have code converters that translate between different digital languages. They are all incredibly good at one specific job. They compute, but they just can't remember. And this is where everything changes. What happens if we take the output of one of these circuits and we feed it back into the input? Well, we create a loop. We introduce the element of time, of history, and just like that, we create memory. This feedback loop is the absolute secret sauce. You see, by taking a result from the past and literally feeding it back into the present calculation, the circuit suddenly has a state. It has a history. It's no longer just reacting to the now, it's evolving based on its own past. And that gives it the incredible ability to store information. Now, this can happen in two different ways. Asynchronous circuits, they change state the very instant an input changes. It can get kind of chaotic, like a conversation where anyone can just interrupt at any time. But, and this is key, almost everything you use today is synchronous. These circuits march to the beat of a drummer, a system clock. State changes only happen on the tick-tock of that clock. It makes everything orderly, predictable, kind of like a perfectly choreographed dance. So if sequential circuits are where memory lives, then we need a place to store each individual piece of that memory. We need a tiny little house, a home, for every single 0 and 1. And that brings us to the hero of our story, the flip-flop. This quote really says it all. The flip-flop is the fundamental building block of memory in pretty much all digital systems. Everything from the registers in your computer's CPU to the RAM in your graphics card is just built from millions or even billions of these tiny, tiny elements. What makes a flip-flop work is its bistable nature. Bistable just means two stable states. Think of a light switch that's designed to be either fully on or fully off. No dimmer, no in-between states. A flip-flop can be forced into a state that represents a 1 or a 0, and it will reliably latch on to that state, just holding it steady until the next clock signal comes along and tells it to check its input again. This little circuit is the physical embodiment of a single bit of memory. Okay, let's break down this table for the most common type, which is the D flip-flop. D just stands for data. Look how simple but powerful this is. When the clock signal rises, that's what that little arrow means. The flip-flop takes a look at its D input. If it sees a 0, the output Q becomes a 0. If it sees a 1, Q becomes a 1. And here's the magic. At all other times, when that clock isn't rising, it doesn't matter what's on the D input. The flip-flop just holds its value. It ignores everything else and just remembers. It's a perfect little memory cell. A single flip-flop storing 1 bit is cool and all, but the real power, the real magic, comes when we start linking them together. By connecting the output of one flip-flop to the input of another, we can create much more complex circuits that do amazing things, like counting. So let's give ourselves a little challenge. We're going to design a counter, but not just a simple 0, 1, 2, 3 counter. Nah, let's make it interesting. We want a custom sequence. It should count from 0 to 1 to 2, then jump all the way to 4, and then loop right back to 0. This is going to require some pretty precise control over our little memory elements. Now, I know this might look super complicated, but what's so amazing is that there's a systematic 5-step recipe to build pretty much any custom counter you can dream up. You figure out how many flip-flops you need, you map out the journey from one number to the next. The real magic happens in steps 3 and 4, where you basically calculate the exact combination of logic gates needed to force those jumps to happen perfectly on each tick of the clock. It turns a creative idea into a concrete engineering blueprint. All right, so that's the theory. But of course, moving from these perfect, neat little logic diagrams to building real, high-speed silicon that actually works, well, that introduces a whole new set of challenges that engineers have to solve every single day. Remember step 4, where we had to simplify the logic? Trying to do that by hand with complex equations can get really messy, fast. That's where clever tools like Karnaugh maps come in. A K-map is this brilliant graphical method that lets engineers use their human pattern recognition skills to find the simplest possible circuit design. And simpler means a smaller, faster, and more power-efficient chip. It's a huge win. And remember our choreographed dance? For that to work, the beat of the clock has to hit every single dancer at the exact same instant. But in the real world, electricity isn't instant. Clock skew is what happens when that clock signal gets to different flip-flops at slightly different times. We're talking delays of a few trillionths of a second, but that tiny, tiny difference can cause the entire system to fail. Managing this is a multi-billion-dollar obsession for chip designers, because if you get it wrong, nothing works. Game over. And that brings us right back to where we started. We've seen how a simple little circuit can learn to remember a single 0 or 1 using a flip-flop. So the next time you look at your phone or your computer or your tablet, think about that. The gigabytes of memory and storage, they're just an unimaginably vast collection of these simple, elegant logic loops, all dancing in perfect time to the beat of a clock. So, how many billions do you think are working for you right now?